Hello everyone, my name is Noor-e, and this is my lab report on constant velocity. In this lab, we are tasked with analyzing one-dimensional motion with constant velocity. The purpose of this lab is to allow us to observe real-world motion at constant velocity. This will allow us to analyze motion of object using tracker, and we will be building computational models and comparing those computational models with our own observations. So the underlying physics concept that we need to understand while observing motion of an object at constant velocity is Newton's second law, which is known as the momentum principle. What's the momentum principle tell us? Well, the momentum principle tells us that the change in momentum of an object is equal to net force times the time interval over which it is applied. And so with some algebra, we can rearrange this equation to predict the motion of an object, and we arrive at a new equation, which is known as the velocity update formula. The velocity update formula the final velocity is equal to the initial velocity plus the acceleration times the time interval. So what does this tell us? This tells us that if the net force is zero, then we already know that acceleration is equal to F net over m. So that means that F net over m is equal to zero, which makes the acceleration equal to zero, which makes the time t times acceleration equal to zero. So that makes Vf equal to Vi. So the initial velocity is equal to the final velocity. So my procedure is that we will record an object in motion with constant velocity. We will then analyze its motion utilizing tracker and extract its position time data. We will then create a computational model using GoScript and predict the analytical position time data. We will then compare our experiment with our computational data using a graph. This is the video that we analyze in Tracker. In our experiment, we can see that the system is our card and our surroundings is everything outside the card. Here we set the time interval in which the object is moving at a constant velocity. We set the calibration stick to calibrate the measurements and set the origin of our coordinate system as the center of the mass of the card. We then extracted this data and used it for our graph. This is the code I used to construct the computational model. Here I set the initial position of the ball at the origin, which is at 0. I calculated the initial velocity by using the position at the first and second time steps and plugged them into the formula delta r over delta t, which allowed me to get the initial velocity. Then I used a while loop and I implemented Newton's second law into the code to update the velocity. Then I used that updated velocity and I plugged it into the position update formula to get the position at each iteration. Delta t was already set to 0.01, which is small enough to allow for accurate computations. And here we can see that the on the velocity time graph, the velocity isn't changing because we can see that the slope is 0. So the velocity is constant throughout the whole motion of the object. However, the position is changing linearly. So it's changing constantly with a constant velocity. As we can see, our observed data is slightly higher than the predicted data from our computational model. There are a few reasons this could have happened. Since our object was a car on a track, it minimized friction compared to other objects in motion, such as a rolling ball or markers in motion. One likely reason the observed data is higher is due to calculation errors. Our initial net force may have been slightly larger than the constant velocity assumed in the model. The computational model represents a perfect constant velocity, but in reality, it's more likely that the car started a bit faster and then maintained that speed across the track. Some of the possible sources of error in our lab were calculation errors, tracker errors, and forces not included in our model. First, while our car had minimal friction, we can't completely ignore air resistance, which is still acted on the car and slightly slowed it down. Another major source of error was in calculating the initial velocity for our computational model. This mistake led to differences we saw between the experimental model and model graphs. Lastly, tracking the video introduced error, because each point we clicked in Tracker wasn't always perfectly centered on the card. These small inaccuracies add up and can make the slope appear slightly different. So here are some additional questions to think about. What if the positive x and the negative x axes were switched? In that case, if the axes were switched, then the slope of our graph would be negative. Other than that, we would not see any other changes. Is the net force really zero? Our net force is not in fact zero because of other forces such as air resistance, which are acting on the cart while it is moving and slowing it down as a result. In this lab, we confirmed that an object moving with constant velocity produces a straight line position time graph. Our experimental data and computational models both showed this linear trend, supporting Newton's first and second laws. While the experimental velocity was slightly higher than predicted, the difference can be explained by factors like air resistance, small calculation errors, and tracking uncertainty. Overall, the lab demonstrated how physics models can accurately describe real-world motion even when small sources of error are present.